The Racer 2 is a micro FPV camera from Runcam, which is said to be designed as a camera for racers. The Runcam specifications for the camera states super wide dynamic range, a 16:9 aspect ratio, 143 and 160 degree field of view, depending on lens type, both PAL and NTSC support, and a 6 millisecond output latency response time, all in a package weighing only 5.5 grams, which is actually a little less, weighing in at 5.464 grams. In this video, we will put this camera through a wide variety of technical testing and specification validation, including picture quality testing, raw electrical latency testing, dynamic range testing, and other tests I believe will help you determine how well this camera will perform. You'll notice some additional testing, as well as some improvements and refinements to my previous methodology in this bench test.
Recursion Labs. For science.
We will start with basic power consumption and efficiency testing. Connected to my bench power supply, we will see how much power this camera consumes at 12 volts, which is a nominal voltage for a 3-cell battery. At 12 volts, the average power consumption is 33 milliamps, which is only 396 milliwatts of power. Bringing the voltage up to 30 volts, the current drops to only 12 milliamps, which is actually a little less at 360 milliwatts, indicating that not only is this camera efficient when it comes to power requirements, it also has efficient power regulation. The second part of this power test is to determine how much heat this thing generates under nominal load. For this, switch to thermal vision. I was a bit concerned with the plastic enclosure at first, but in the span of 5 minutes, this camera slowly heats up to less than 50 degrees Celsius. This might be a temperature you personally wouldn't want to fly under in the hot summer sun, but this camera is definitely comfortable at this temperature, and I see no problems with either of these tests. I have placed the camera in a box to isolate all outside light. The video output of the camera is tapped with my oscilloscope, where you can view the raw analog signal with clear frame separation on the scope. An all-black output shows up as a lower overall voltage, where an all-white would be a higher overall voltage. I have a push button on my test board which supplies voltage to the LEDs, turning them on. The path from the button to the LED is also tapped with my oscilloscope, so that voltage spike when the button is pressed can be clearly measured. The difference on the oscilloscope from when the voltage spikes when the button is pressed to when the analog signal spikes from the white bright light will be the camera latency. Runcam claims this camera has a 6 millisecond latency, but the latency testing I performed has determined that they were actually very wrong here, by more than 400%. Before you get angry at Runcam and look silly, to my surprise, the latency was actually 400% better in testing than they claimed. At a consistent 1.5 millisecond latency measurement, the latency did not change and remained consistent over hundreds of samples using NTSC, making the results here very firm. Not only was the latency impressive for the raw latency test, the response time measurement for when the light was turned off and the entire picture went black came in at a consistent 1.6 milliseconds, meaning that the latency of this camera is not only consistent, you can be reasonably confident that it will be consistent in all conditions. Testing the latency in PAL, which using a traditional LCD method is always higher, was actually lower at 1.24 milliseconds, which also remained consistent for hundreds of tests. This wouldn't compensate for the higher latency between frames due to having 50 frames per second versus 60 frames per second with NTSC, but it is interesting to see it less regardless. I wonder if it has something to do with the camera CPU being utilized less due to the lower frame rate. Regardless, if you choose PAL over NTSC, you're saving 26 microseconds from the camera itself. To put things into perspective, this camera has 16 to 33 times less latency than the Cadex Ratel, which has the equivalent latency difference to 1.2 to 2.7 times that of the difference between S-Bus and PPM, which at the time was considered a massive improvement. This camera will definitely be used as a reference for any future camera reviews when it comes to latency. For some reason, this camera did not come with a control board to configure the camera, which forces you to have one already or to use a compatible flight controller to configure the camera. I made a custom image with distributed equally sized squares and circles to test how the camera may distort the perspective of the image over the surface of the lens. The fisheye effect comes as expected for the field of view of this camera, but the image appears to have a correct perspective across the image. If you're running a screen with a 16:9 aspect ratio, you need to enable widescreen mode to ensure the perspective is correct for your screen. Next, we will observe how good the image quality of the camera is against a standard camera test image displayed on my bench monitor. Focusing only on the negatives, you'll notice that the red comes in as more of an orange, and some of the colors appear to be brighter than they should. The white shows some color pixel artifacts at the edges. Outside of that, the rest of the image looks good for the resolution we are using. Since this camera came with a 2.1mm lens, the advertised FOV is 125 degrees. Putting the camera into the center of a large printed protractor, we can use the FPV feed and a straight object to determine the angle the camera can see. At the center edge, the field of view measured at 110 degrees, which is 15 degrees less than advertised. However, you'll notice that the upper corner has additional FOV due to the fisheye, and measuring the uppermost corner comes in at 140 degrees of view, so it may be fair to say that the range is between 110 and 140 degrees, with 125 degree average, which is what they have it rated as. Now, for the low light test. I've significantly improved how the this test is conducted, by constructing a diffuse light which can adjust brightness with as little as 10 millivolt increments, while being able to produce extremely low amounts of light. The idea is to evenly distribute the light over the lux meter so that both the screen and the lux meter sensor are seeing the same amount of light, allowing us to visually measure the visibility to lux. Without having your own lux meter at your fly spots, this is more useful for comparing cameras between each other. At 0.3 lux, which is the light on the surface from the moon at full brightness, it is difficult to see anything. At about 2 lux, the camera can clearly start seeing objects, and between 3 to 4 lux, everything is perfectly viewable. For the sun emulation tests, I put my small 900 lumen flashlight at a distance that would take about the same space on the camera as a sun would to see how the camera will respond. Outside of a lens flare and a bright halo around the light source, the rest of the bench is clearly viewable. For an extreme test, I took my 5000 lumen flashlight up close and turned it on and off repeatedly to see how the camera would respond. The image went gray when the light was on due to the close proximity and the amount of screen real estate the light took up. You can observe how long the camera took to recover once the light was turned off, where the first frame is completely black and subsequent frames the camera recovers to normal state. While performing these tests, I realized that this camera reminded me a lot of the Runcam Micro Sparrow 2, which I have on one of my 3-inch quads. I didn't perform tests on this camera because it is now discontinued, but my curiosity got the best of me, so I pulled it out to take a quick look. The latency of this camera turned out to be the exact same, at a consistent 1.5 milliseconds of latency. While I only performed a few of the same tests, on paper it looks like these cameras are very similar, with the exception of the Runcam Racer 2 having improved firmware. If you like the Runcam Micro Sparrow 2, then you'll probably love this camera even more, since it appears to be the Micro Sparrow 4, except Runcam rightly decided to move away from confusing bird names and instead appropriately name this camera for what it's for. The Runcam Racer 2 lives up to its name, with a latency that should make any racer or pilot that enjoys the flight characteristics of faster response times extremely happy with this camera's impact on your overall latency. This camera does not have perfect color reproduction, and does have some digital color artifacts at the edges of the whites, but it gets them close enough that it should not hinder your flight experience. The widescreen perspective is great, and the field of view is acceptable for being able to see objects in your peripheral vision, and has the option to go with a wider field of view lens if you prefer. This camera should be able to handle flying in both low light situations such as indoors and dusk, as well as being exposed to direct sunlight with a little bit of light halo and lens flare to hinder your view. I have not reviewed enough cameras to state that this is the perfect camera for racing, but I would definitely love to use this as a benchmark against other cameras moving forward. A special thanks to Rotorev in Mississauga for lending me their floor model for this review. Due to the results of this testing, I've ended up buying it off them anyways. I'd love to hear your feedback for these tests, and feel free to suggest any other cameras that you think I should do next, especially if you think they would perform better than this one. I have some other non-camera latency tests in the works I will hopefully be able to share with you in the next few weeks. If you're interested in latency testing, you should definitely keep an eye out for them.